All right, today we're going somewhere a little different. We're heading to the cosmic graveyard. We're on the hunt for one of the most common and honestly one of the most haunting objects in the entire universe.
I mean, think about that for a second. The ghosts of dead stars. It's such a powerful, poetic way to put it, right? Because we're not just talking about some inert ball of rock. These are the lingering spirits of stars that once lit up the night sky.
So that begs the question, right? What does a star's ghost actually look like? What kind of secrets is it holding? Well, we're going to find out. We'll dive into what they're made of, how we even found them in the first place, and what they tell us about the ultimate fate of everything, including, our very own sun.
Okay, so just how common are these things? We'll get this. Over 97% of all the stars in our galaxy are going to end up this way. This isn't some rare, bizarre object. This is the normal final chapter for almost every star out there.
So let's get down to it. What exactly is a white dwarf? Well, for starters, it's not really a star anymore. The best way to think about it is like a stellar ember. You know, like the last glowing bit of charcoal in a campfire? It's the super dense core that gets left behind after a star has burned through all its fuel. There's no new energy being made. It's just glowing from leftover heat, slowly cooling down over billions of years. And the way we first found these things, it's like something out of a detective novel, a real cosmic whodunit. Because the very first one we ever identified, we couldn't even see it, but we knew something was there because we could feel its gravity. The whole story kicks off with Sirius, the brightest star you can see at night. Way back in 1844, an astronomer named Friedrich Bessel saw that it was wobbling. Just a tiny bit, but enough to suggest something massive and invisible was pulling on it. It took almost 20 years, but then Alvin Graham Clark finally saw it, a teeny, faint dot of light right next to Sirius. But here's where it gets really weird. In 1915, they analyzed that little dot's light and found out it was insanely hot, but it was also super faint. And that was the big mystery, the paradox that didn't make any sense. How could something be massive enough to yank around the brightest star in the sky, but also be so incredibly tiny that it was barely visible? It had to be massive, but also small, hot, but also faint. Solving that puzzle forced astronomers into some really mind-bending new territory about what matter can do. All right, to solve that paradox, we have to go inside one of these stellar corpses. And I'm telling you, this is where the laws of physics they get weird, like really weird. This is what happens when the universe cranks the pressure dial all the way up to 11. So here's what they figured out. Imagine taking our sun, the entire thing, all of its mass, and squishing it, crushing it down until it's the size of planet Earth. That's what a white dwarf is. The sheer density it's almost impossible to wrap your head around. We're talking about a density of about 1 million grams per cubic centimeter. Now, that's just a number. It doesn't really mean much, right? So let's try to make it make sense. Get this. If you could somehow scoop up a single teaspoon of this white dwarf material and bring it to Earth, it would weigh several tons, as much as a full-grown elephant. That's how insanely packed this stuff is. So you have to wonder, what's stopping gravity from just crushing it down even further into a black hole? The answer is something straight out of quantum mechanics. It's a force called electron degeneracy pressure. Okay, so in a normal star like our sun, the outward push from nuclear fusion fights against the inward pull of gravity. But a white dwarf has no fusion, right? It's dead. So instead, the matter gets so compressed that all the electrons are basically touching. And there's a fundamental rule in quantum physics that says you can't cram them any closer. They just push back. And that push is strong enough to stop gravity dead in its tracks. It's wild. So, okay, these things are super dense, super weird quantum objects. But they're more than just a cosmic curiosity. Turns out, these stellar ghosts are one of the most important tools we have for figuring out some of the biggest secrets of the universe. But even that incredible quantum pressure has a breaking point. There's a hard limit to how much mass it can support. It's called the Chandrasekhar limit, and is right around 1.4 times the mass of our sun. If a white dwarf ever gets heavier than that, well, gravity wins. And what happens next is one of the most violent and spectacular fireworks shows in the entire universe. Picture this. You've got a white dwarf orbiting another star. It acts like a cosmic vampire, slowly siphoning off gas from its partner.
It just gets heavier and heavier, inching closer and closer to that 1.4 solar mass limit. Once it hits that tipping point, it's game over. Gravity overwhelms the quantum pressure, the whole thing collapses in on itself, and triggers a runaway thermonuclear explosion that completely obliterates the white dwarf. We call this a Type A supernova.
Now here is why this is so unbelievably important. Because these explosions always happen at the exact same mass, they all have the exact same intrinsic brightness. They are perfect standard candles. It's like having a 100-watt light bulb that you can see across the universe. By measuring how dim they appear, we can tell exactly how far away they are. And it was by using these standard candles that astronomers made one of the most staggering discoveries of all time. The universe's expansion isn't slowing down, it's speeding up. And that discovery is what led us to the idea of dark energy.
So all of this might sound like it's happening a long, long way away. But this whole story, it's also a prophecy. It's a sneak peek into the very, very distant future of our own home, our own solar system.
So here's what's going to happen. In about 5 billion years, our sun is going to swell up into a massive red giant. Then, its outer layers will drift away into space, forming this absolutely beautiful glowing shell of gas we call a planetary nebula. And what's left behind? Right in the middle of it all, the sun's hot, dense core. Our sun will become a white dwarf, the final glowing ember of our star, destined to cool for trillions of years. And just to give you a sense of the insane timescales we're talking about, that cooling process is so slow that in the 13.8 billion years the universe has been around, not a single white dwarf has had enough time to cool down completely and go dark. Not one. Every single one ever formed is still glowing out there somewhere. It's kind of amazing to think that our universe is still too young for its oldest ghosts to have truly faded away. Which leaves us with one final, kind of haunting thought. Long, long after the Earth and all the other planets are gone, the cooling corpse of our sun, our star's ghost, will still be there. A silent witness to our entire solar system's history. So you have to wonder, what secrets will our sun's ghost tell? Could some future astronomers, billions of years from now, analyze its light and find the chemical traces of Earth? The ghost of our star might just be our most enduring legacy.